Good morning, students. In the previous lecture, we started to discuss about Laplace transform, and we have seen some examples. Just to refresh the previous lecture, we have two types of signals, right-sided and left-sided signals. And if you remember, we derived the Laplace transform of the right-sided signal, which is e to the power of at ut. This is right-sided because of the unit step function ut. The Laplace transform will be 1 over s plus a, and the region of convergence is real of s greater than minus a. So we have the S plane having a real axis and j omega axis. The real axis is the sigma axis, and the j omega axis, the y-axis is j omega axis, so greater than minus a. And we have the left-sided signal, which is minus e to the power of minus 8 u minus t. This is left side because of u minus t. And the region of convergence real of s less than minus a. So what's the difference between these two is their region of convergence. So today we will further study about region of convergence and some properties of Laplace transform. Some signals do not have Laplace transform since they have no region of convergence. For example, if you have x of t is equal to c times e to the power of minus t for all t, then if you remember from the definition, for the Laplace transform to exist, the absolute value of x of t multiplied by e raised to sigma t dt, this should be absolutely integrable. That means from minus infinity to infinity of the integration of this should be less than infinity. But for this signal, because it is for all t, it is equal to infinity for all sigma. So there is no region of convergence. And for example, another signal x of t e raised to j omega naught t. This one from our study in Fourier transform, x j omega is 2 pi Dirac omega minus omega naught. However, if we try to see the Laplace transform does not exist, to check this, again, the integration from minus infinity to infinity x of t e raised to minus sigma t dt, and because of the absolute value, when we take the absolute value of e raised to j omega naught t, it is 1, so it will be the integration from minus infinity to infinity e raised to sigma t dt. Again, this will be infinity, whatever sigma value we have. So the Laplace transform does not exist. The region of convergence is, in fact, it consists of a collection of parallel lines, parallel to the j omega axis. It only depends on sigma. It only depends on sigma. Why? Because, again, the Laplace transform of this means the integration, and then if we check the absolute integrability condition, it is from minus infinity to infinity x of t times e raised to sigma t dt. So there is no j omega condition here, the omega condition. So it only depends on sigma, which is real of s. If x of s is a rational function of s, that means I have a numerator polynomial n of s over denominator polynomial d of s, then the region of convergence does not include the poles. Why? Because at the poles, x of s will be equals to infinity. The pole means the location where d of s is equal to 0. So if you divide by 0, it will be infinity. So x of s is not convergent, which means the region of convergence does not include the poles. If x of t is finite duration signal and absolutely integrable, then the region of convergence is the entire S-plane, which means if, for example, I have a signal x of t from minus T1 to T2. Okay, this is from minus T1 to T2. Then if I check the condition of absolute integrability, then it is from minus infinity to infinity x of t raised to minus st dt. Again, this one, if you multiply by e raised to sigma t minus sigma t, it is always the integration is always less than infinity. That means the Laplace transform exists, or the region of convergence also exists. If x of t is a right-sided signal, what is a right-sided signal? A signal which starts at a certain time and at a certain time t and goes to the right. That means, or it is zero before some time t. Then, if real of s is equal to sigma naught is in the region of convergence, then all values of s, all sigma, which are greater than sigma naught, are also in the region of convergence. So if sigma naught is in the region of convergence, all sigmas greater than sigma naught are in the region of convergence. Because for the right side signal, the region of convergence starts at a certain, for example, sigma naught and goes to at a certain sigma naught and goes to the right. That's why. So right side signal means here it starts at T1 and goes to, for example, positive infinity. Left side signal. For left side signal also means a signal which starts from some time t1 and goes to the left. For this case is also, if the region of convergence sigma naught is in the region of convergence, if real of s is equal to sigma naught is in the region of convergence, then any value of sigma which is less than sigma naught will be also in the region of convergence. So for example, if sigma 1 is less than sigma naught, it will be in the region of convergence, which means for the left side signal, the region of convergence starts from a certain value of sigma naught and certain value of sigma naught here and goes to the left. What about two-sided signal? A two-sided signal means which exists from minus infinity to infinity, for example. So it starts from time. We have the right side part starting from, we can break it into the right side part starting from t naught goes to the right, and left side part starting from t naught goes to the left. So the region of convergence of such kind of signal is a stripe in the S-plane. A stripe in the S-plane means, for example, for the right-sided one, it starts from sigma r and goes to the right, and for the left-sided, it starts from sigma l and goes to the left. So if we see the intersection or the common region between the two will be a stripe which is between sigma r and sigma l. Okay, so like this, for example, this is right-sided, starts from sigma r for the right-sided part and goes to right, and left side starts from sigma l and goes to the left. The intersection between these two is the stripe here. If x of s is rational, then its region of convergence is bounded by poles or extends to infinity. Yes. In addition, no poles of x of s are contained in the region of convergence. Why? Because at the poles, x of s will be infinite. So x of s will be infinite, does not include the poles. If x of s is rational, then if x of t is right-sided, the region of convergence is to the right of the rightmost pole. That means if x of t is right-sided signal and if it has several poles, for example, here I have a signal x of t having two poles, one pole here, another pole here. So the value of the pole at this one is greater than the value of the pole at this. Therefore, the region of convergence will be to the right of the rightmost pole. So always it will be to the right of the rightmost pole for the right-sided signal. On the other hand, for the left-sided signal, it will be to the left of the leftmost pole. So this is left-sided signal. So it has two poles, for example, here and here. So the leftmost is this one. So the region of convergence will be to the left of the leftmost pole, like this. Now, if it is two-sided, then we have the intersection between the two regions will be a stripe like this. Now, one thing that we have to know, if the stripe includes the j omega axis, if the region of convergence includes the j omega axis, what is the j omega axis? The j omega axis is sigma is equal to 0. So if it includes the j omega axis, then we say the Fourier transform of x of t exists. So if, for example, we are given a certain problem and we are asked to find the Laplace transform, after we find the Laplace transform, and if we are asked, does this signal has Fourier transform, does it have a Fourier transform, then we check whether the region of convergence includes the j omega axis or not. Based on that, we can say the Fourier transform exists or doesn't exist. All right, now suppose I have a problem like this, and this problem is open, so open-ended problem. We say this x of s is s plus 3 over s plus 1 is s minus 2, and we are asked to find x of t. But here, the region of convergence is not given. So we need to find the inverse Laplace transform case by case. That means considering different region of convergence. Now, when we see this signal has poles at -1, at 2, and zeros at -3, and another 0 at infinity. So what are the three possible region of convergence? The three possible region of convergence are one less than -1, the other between -1 and 2, the other greater than 2. So I have three possibilities. Based on this, I should say about the type of the signal I have corresponding to the inverse Laplace transform of x of s. Okay, before I do that, to find the inverse Laplace transform, I do partial fraction expansion. So I have here a over s plus 1, b over s minus 2, which is a is -2 over 3 and b is 5 over 3. So maybe I have it here in the class notes. Let me check. I think it is the same problem. So s plus 3 is plus 1 is minus 2. So I do partial fraction expansion here. A over s plus 1, b over s minus 2. So a times s minus 2, b times s plus 1. And then we group the same terms like as and bs, a plus b times s, and minus 2a plus b. Then from here, we check the numerator. The numerator is this one, s plus 3, with this one. We check these two, and we compare. So the coefficient of s is here 1. So a plus b should be 1. And the constant part is minus 2a plus b. Then minus 2a plus b is equal to the constant is 3. So then we solve these two. Of course, how we solve it? Either we do substitution of one variable or write one variable in terms of the other in the first equation and put it in the second equation, or we just directly eliminate the variables because it is simultaneous equation, two equations with two unknowns. So for example, here if we subtract the first the second from the first. So a minus minus 2a 3a, b minus b 0, 1 minus 3 negative 2, then a will be minus 2 over 3, then b is 1 minus a, which is 5 over 3, and we have this. Now this is, let's say this is x1s and this is x2s. X1s has two options. Okay, it can be either a right-sided signal, that means the region of convergence greater than minus 1, or left-sided signal, the region of convergence less than minus 1. The same x2s has two options, the region of convergence greater than 2 and the region of convergence less than 2. So we check these conditions. So we can have all the possibilities here. The first one is, let's say x of s has region of convergence less than negative 1, which means both for x1s and x2s less than negative 1. So that means x1s should be a left-sided signal. Why? Because if it is less than minus 1, then this is a left-sided signal from our previous study. So for that case, then we use, remember, the rule of the two rules. What are the two rules? I go back again. If I have e raised to x of t e raised minus for the right-sided, if I have x of t e raised to minus at ut, then the Laplace transform is 1 over s plus a, real of s greater than minus a. And the left-sided, this one, minus e raised to minus atu minus t. Again, Laplace transform 1 over s plus a, real of s less than minus a. So we have these two conditions. Okay, so based on that, this is left-sided, means if we use the previous rule, then this will be 2 over 3 e raised to minus t u minus t. Okay, what about the second one? To fall its region of convergence under this means under sigma less than minus 1. The second one, the region of convergence for the second should be also less than 2. So that region of convergence less than minus 1 intersection region of convergence less than 2 will be region of convergence less than minus 1. This is the common for both. Therefore, the second signal should be also left-sided. So left-sided means when I change it to time domain, minus 5 over 3 e to the power of 2t u minus t. So the two signals, both signals are left-sided. Then I combine these two and I get this. This is for the first case. For the second case, region of convergence between negative 1 and 2. Between negative 1 and 2, therefore for this one, okay, twofold its region of convergence under this, under negative 1, between negative 1 and 2, to be under between negative 1 and 2. What should be the case? The case should be this should be right-sided signal greater than minus 1. So it should be greater than minus 1. So the first one greater than minus 1. And what about the second one? The second one is less than 2. So less than 2 means left-sided. So the first one right-sided, second one left-sided. And for the two, the common will be the two signal. When I combine the two signals, it will be minus 2 over 3 e raised to minus t ut minus 5 over 3 e raised to 2t u minus t. And the last one, region of convergence greater than 2. Greater than 2 means both should be right-sided. x1s and x2s. Both should be right-sided. So that means the first signal minus 2 over 3 e raised to minus t, and the second 5 over 3 raised to 2t ut. Now, if we see these three cases, for which one the Fourier transform exists. For which signal? Remember, the Fourier transform exists if the region of convergence includes the j omega axis. J omega axis means between -1 and 2. So between -1 and 2, the region of convergence, if the region of convergence is between -1 and 2, then the Fourier transform exists. So the signal will be case 2. If we see the signal for case 2, we have this signal, which is exponentially decaying signal. And the second one is also decaying. Why? Because U minus T. U minus T means left-sided. So the overall signal is decaying. So that means the Fourier transform exists. By the way, if we see the first case is 2/3 raised to minus T. This one, when T is going to negative infinity because of minus T, this will be exponentially growing. And this is decaying, the second is decaying. So overall, it is growing signal. That means the Fourier transform does not exist. And for the last one also, if I have the last part is this is decaying, and this one is growing, and overall it's growing, and the Fourier transform doesn't exist. So the only case where the Fourier transform exists is between -1, when the region of convergence is between -1 and 2. All right. So we did already this. We continue now. Calculation of inverse Laplace transform. How do we calculate the inverse Laplace transform? Okay. This is the original equation of Laplace transform. As you see, actually the Laplace transform is the Fourier transform of x of t e raised to the power of minus sigma t. Therefore, x of t e raised to minus sigma t will be this integration. Okay, and if we say s is equal to sigma plus j omega, and if we substitute for d omega ds over j, then the inverse transform formula will be this one. X of t is 1 over 2 pi j from sigma minus j infinity, sigma plus j infinity, x of s e raised to st ds. This integration is, we call it contour integration. It's complicated. It may not be easy. So instead, in this course, we will study how to get the inverse Laplace transform using partial fraction expansion. So the partial fraction expansion means the one we explained before. For example, for this case, we did it already. We have a over s plus 1, b over s minus 2, and then we determine left side, right side by using this rule, and we get the inverse Laplace transform using partial fraction expansion and the rule of left-sided and right-sided signal. All right, this is the same thing now. Okay, let's talk about some of the properties of Laplace transform. The simplest one is linearity. If I have ax1t plus bx2t, then the Laplace transform is ax1s plus bx2s. What about the region of convergence of the overall signal? The region of convergence will be the intersection of the region of convergence of x1s and the region of convergence of x2s. Region of convergence can be bigger due to pole zero cancellation. That means bigger than one of them. So if the region of convergence of one of them is R1, the other one is R2, normally it is R1 intersection with R2, but it can be bigger for if there is pole zero cancellation. Here there is one simple example. For example, if I have x1 t is equal to x2 t and a is equal to minus b, then x of s is equal to 0. Of course, for x of s is equal to 0, the region of convergence is the entire S plane. Time shift property, this is very important. X of t minus capital T, the Laplace transform is e to the power of minus st times x of s. And the region of convergence is the same as the region of convergence of x of s. Okay. For example, let's take this example and let's find x of t. So I have x of s e to the power of 3s over s plus 2. Real of s greater than minus minus 2. Then what is x of t? Okay. When we see this exponential function, we know that there is time delay or time shift. So first, what we should do, we need to find the inverse of 1 over s plus 2. How we find? Based on the condition of the region of convergence. So what is the inverse of 1 over s plus 2? If real of s is greater than minus 2. From here, we know that the signal is right-sided. Then automatically we know it is e to the power of 2t times ut, right-sided signal. Then we determine the amount of delay t. Here from this relation, capital T is minus 3. So that minus minus it will be 3s. So capital T is minus 3. That means the signal, if it is x of t, it will be x of t plus 3. Minus minus 3, it will be x of t plus 3. So this one will become e to the power of minus 2t plus 3 ut plus 3. So if we have such kind of problem, we just first find the inverse of the rational function. In this case, the rational function is 1 over s plus 2. And if there is exponential function like this, we know that it is time delay. Okay, convolution property. If I have an input x of t and system h of t, yt, h of t convolved with x of t, then the Fourier transform of x of t is x of s. The Fourier transform of y of t is y of s. H of t is, the Laplace transform, sorry. The Laplace transform of x of t is x of s. The Laplace transform of y of t is y of s. The Laplace of h of t, h of s. Then y of s is x of s times h of s. Very important property this. What about the region of convergence of y of s? The region of convergence is at least the overlap of the region of convergence of h of s and x of s. That means the intersection between the two. A region of convergence can be empty if there is no overlap between the two. Region of convergence. That means if there is no overlap between the ROC of h of s and the ROC of x of s, then the ROC of y of s can be empty, which means y of s does not exist, or y of t does not exist in such case. So here, let's say x of t e to the power of t ut, h of t minus e to the power of minus t u minus t. Then the region of convergence of the first one. The region of convergence of the first one is real of s greater than 1. The region of convergence of the second one, real of s less than minus 1. So the common for both does not exist. So that means the region of convergence of y of s does not exist. Region of convergence could be larger than the overlap of the two. In what case? For example, if I have x of t convolved with h of t is equal to Dirac t. Dirac t is the impulse. So we know that the Laplace of Dirac t is equal to 1. So it is the overall S plane. The region of convergence is the overall S-plane. So that means it is greater than the region of convergence of h of t or x of t, unless x of t or h of t sigma t. All right, the other property is differentiation property. If you have, this is the inverse formula. From the inverse formula, if you differentiate this with respect to time, we will get this. Okay, differentiate this with respect to time. Okay, the s part will come and it will become sx of s e raised to st. And if we relate it with this, it means the derivative of x of t is s times x of s. So with the region of convergence containing the region of convergence of x of s. So if I have the second derivative, it will be s squared times x of s. Again, a region of convergence could be bigger than the region of convergence of x of s if there is whole zero cancellation. Let's see this example. X of t ut. What is the Laplace of ut? 1 over s, the Laplace of unit state. And real of s greater than 0. What is the derivative? The derivative of x of t is Dirac t, and it is 1. It is 1, and how we find it, for example, using the derivative property dxt by dt means s times x of s is 1 over s times 1 over s is equal to 1. What is the region of convergence? The entire s plane. So because of the pole zero cancellation. Another very important property is if I multiply the signal by t times e to the power, for example, if I have t times e to the power of 80 ut. Okay, so how we find? From this property, minus t times x of t, the Laplace transform of it is dx of s by ds, or t times x of t, the Laplace transform is minus dx of s by ds. Okay, so for example, if I have this one, t times e raised to 80 ut. First, what is the Laplace of e to the power of 80 ut? It is 1 over s plus a. And if I take the derivative of d by ds with respect to s, remember, so you differentiate the numerator and the derivative and the denominator. Okay, you have to use the rule of the derivative of f of s divided by g of s. Then you will come, the result will be 1 over s plus a the whole square for real of s greater than minus a. Integration property. Integration in property, if x of t is x of s, then from minus infinity to t x of tau d tau is 1 over s x of s. And the region of convergence is the region of convergence of x of s intersection the region of convergence of 1 over s. 1 over s is real of s greater than 0. Initial and final value theorem. These are important. If x of t is equal to 0 for t less than 0, then x of t and x of t contains no impulse or higher order singularities at t equal to 0, x at 0 plus, the value of x at time t equals to 0 plus is equal to the limit as s goes to infinity, s times x of s. And if x of t is equal to 0 for t less than 0, and x of t has a finite limit at t equals to infinity, the final value theorem says the limit as t goes to infinity of x of t is the limit as s goes to 0 of x of s. Okay, so it's just like exchanger here. As the value at t equal to 0 is the limit as s goes to infinity, s times x of s. Here, the value at t is equal to infinity is the limit as s goes to 0 times x of s. Okay, now the next topic, analysis and characterization of LTI systems using Laplace transform and analysis of systems described by linear constant coefficient differential equation using Laplace transform. We'll study it in the next lecture. I hope you understand the examples in this lecture and some of the properties that we discussed. And for further understanding, please read the class notes and also the PowerPoint slides, the PDF file for the PowerPoint slides. Thank you for listening to this lecture.